The first thing I want to do is explain what I mean by Hilbert's Dream, and then we can move on to discussing, and why it was wrecked, and then we can move on to the discussion of whether anything can be salvaged from the wreckage. So by way of introduction, I want to think about the question of what mathematical ingenuity is. And to think about that, I want to think about quadratic equations very briefly. I hope that this will either be, if you're still at school, which I think a lot of people here are, something that's very familiar to you. And if you're not, then at least something that was once very familiar to you, solving quadratic equations. And let's take a fairly easy one. The equation x squared plus 6x plus 2 equals 0. How do we go about solving that? Well, the method of completing the square says, let's begin by just noticing that x plus 3 squared equals x squared plus 6x plus 9, which looks like the x squared plus 6x plus 2, except that the 2 was changed to a 9. And this x plus 3 squared, the number 3, you just choose to be half the 6, and then it all works out, and you get used to that. And now if x squared plus 6x plus 2 equals 0, and x plus 3 squared equals x squared plus 6x plus 9, well, that x squared plus 6x plus 9 is 7 more than the x squared plus 6x plus 2, which we know is 0, from which it follows that x plus 3 squared must be 7. And once you know that, then it's plain sailing. X plus 3 is plus or minus the square root of 7. Subtract 3 from both sides. X equals minus 3 plus or minus the square root of 7. Now, the details of that are not too important to my point, but what is important is that the method there was very systematic. And once you've seen how to do it for 2 or 3 quadratic equations, you can just go ahead and apply it to all sorts of other ones, and even go a little bit further and take coefficients that are letters rather than numbers and get a general formula for the solution of a quadratic. So solving quadratic equations can be done completely mechanically. Here are a few other things that you can do completely mechanically. One of the things one's taught at school is how to add numbers together, subtract, multiply, and divide. You just learn algorithms or mechanical procedures for doing those. Solving quadratic equations I've just discussed. Solving simultaneous equations, there are various different algorithms for that. Calculating areas and volumes, at least of shapes that don't have curvy bits to them, can be done fairly straightforwardly. If you want to calculate a square root to any accuracy, you may not have been taught a method for this at school, but if you wanted to, you could just do it by a sort of directed trial and error. Say you wanted to work out the square root of 2. You say, well, 1 is too small, 2 is too big, 1.4 is too small, 1.5 is too big, so it's between 1.4 and 1.5. You just keep going like that, getting more and more digits of the square root. Differentiation of functions of this kind you can do, again, systematically. Solving cubics and quartics is something you definitely don't get taught at school, but it just happens that that can be done systematically. It's much more difficult than solving quadratic equations. Solving quintic equations, famously, they don't always have solutions, or not of the kind that one's looking for when one solves quadratics, cubics, and quartics. However, when they do have solutions, people know how to find those solutions. And finally, a similar thing happens with integrating. One of the things one sees fairly early on is that there are functions like e to the minus x squared that you can't find a function that differentiates to that, or you can't find a nice-looking function with a formula that differentiates to that. But when there is such a formula, it can be found, although it can be a little bit tricky. So having seen that, it's tempting to ask, and this question occurred to the mathematician David Hilbert a little over 100 years ago, of whether actually one could do the whole of maths purely mechanically. Could you just, let me just be a bit more, well, before I move on to exactly what that question means, let me just consider one case that might make one pause for thought a little bit, which is Diophantine equations. So Diophantine equations are just like ordinary equations, except that you stipulate that the solutions always have to be whole numbers. So the equation 2x plus 3 equals 6 is easy to solve. X equals 1.5. But if you insist that x is an integer, then it doesn't have a solution. So if something's a Diophantine equation, it becomes much less obvious whether it has a solution or not. So here's an example. The equation 8x plus 11y equals 250. If those were any numbers, then you could just choose any y you like. take 11y away from 250 and divide by 8, and that would be your x. But if x and y have to be integers, then it's much harder to find solutions, although in this particular case, there are systematic methods for doing so, which I won't go into. What about all solutions to x squared plus y squared equals z squared? Again, if they're just ordinary real numbers, that's very easy to do. But if they have to be integers, then they somehow have to be special triples of integers, things like 3, 4, 5, 5, 12, 13. And mathematicians now have an understanding of what all so-called Pythagorean triples are. More generally, there's a pretty good understanding of what the solutions of x squared plus y squared equals m are. In particular, we know for exactly which m can be written in the form x squared plus y squared with x squared and y, well, with x and y both integers, positive integers actually, integers. X to the n plus y to the n equals z to the n. We also know what all the solutions to that are. The answer is, if n is 1, then it's easy to do it. If n is 2, then we've already discussed it. And if n is at least 3, then there are no solutions apart from the boring ones where 1 of x and y is 0. But the fact that there are no solutions when n is 3 or above is a very, very famous theorem called Fermat's last theorem, even though it was proved by Andrew Wiles. And finally, the equation x to the m minus y to the n equals 1. This is the so-called Catalan conjecture. One solution is 3 squared minus 2 cubed. That's 9 minus 8. Gives you 1. And for a long time, it was an unsolved problem whether there were any other solutions. Can you find any other powers that differ by exactly 1? And the answer turns out to be no, you can't. That 9 minus 8 is the only solution to this Diophantine equation. But that's a very difficult result that was proved only recently. So the main thing I want to emphasize here is the methods that have been used for those problems are extremely different. And it seems once you've seen those methods, you start to lose faith in the idea that there might be a systematic procedure for solving all Diophantine equations. And in fact, it turns out that there isn't. I'm slightly giving the game away there. But so what was Hilbert's dream then? More precisely, what you want is, nowadays actually we can describe it in a way that Hilbert couldn't. We can just say, because we've got computers, so we can think of a mechanical procedure as just something that you can program a computer to do. So in terms of computers, so the black box that I've put there, one can think of as a computer. So what you want to do is you feed into the computer in a language that your computer understands some mathematical problem, and in Hilbert's wildest dreams, the computer would then whir and click for a bit, and out would come a proof or disproof of the statement that you fed into it. So can that be done? Is there some computer program that can solve any math problem that you give to it? Well, the first major blow to Hilbert's hopes came from Gödel, who showed, if to oversimplify a little bit, that there are statements that don't have proofs or disproofs. So you certainly can't have a computer program that will always give you a proof or a disproof, because sometimes it doesn't even exist. But there's an obvious modification you can make to the dream given this development, which is, you say, well, all right then, not all statements have proofs, but a lot of statements do have proofs. So how about just having a computer program that gives you a proof or a disproof if there is one, and otherwise says, sorry, this statement doesn't have a proof or a disproof. So that would still be a very, very nice thing to have. It would put mathematicians out of a job, and at least if it worked reasonably quickly. And so the dream somehow lives on in this modified form until Alan Turing, whose centenary it is this year, and also Alonzo Church independently, demonstrated that there was no such mechanical procedure. This was an amazing achievement of both of them. Turing, in order to do it, he was doing it before there were computers, so he had to say exactly what a mechanical procedure was, and then in fact, that was, in a way, the main thing he did. Once he'd done that, the argument that no mechanical procedure existed for this problem was sort of, nowadays, if you read it, it's reasonably straightforward. But coming up with the precise definition of what a mechanical procedure was very, very clever indeed. However, it's still possible to salvage something from this dream. In a way, we're not interested in proofs that are too long. If a proof would take 1,000,000 years to read, then I don't really care whether it exists or not. I don't care if my computer can provide it or not. So maybe what one should do is say, and perhaps the reason that not all that there isn't a mechanical procedure for finding a proof when it exists is that just some proofs are much too long. So one might hope that you could find a mechanical procedure or an algorithm that you can program into your computer that takes a slightly modified input. It takes a mathematical problem and a number n, and now what it gives you is a proof of length at most n, whatever that means, but you can come up with some, maybe it uses at most n symbols or something like that, if it exists, and otherwise it tells you that no such proof exists. So either it gives you a shortish proof, or it says, sorry, there isn't a shortish proof of this result, or disproof, of course. And, well, I have some good news, but there is such a procedure. However, whenever you see the phrase good news, it's nearly always accompanied with by some bad news, and that's the case here. So the problem is, so let me just describe to you a method for determining for any math problem whether there is a proof that uses at most n symbols. You just get your computer to print out all possible sequences of n of the symbols that you have and just read it and see whether it's a valid proof of the statement that you were trying to prove. That can be done purely mechanically. The trouble is that if n is big enough to fill, say, a 10-page paper, then the number of strings of symbols that would fill a 10-page paper is so large that getting this program to run would take much, 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 much longer than the universe has existed, even with all the fastest computers in the world cooperating and so on and so forth. So you can't actually use this brute force algorithm. And actually, that's not the end of the story. I've just told you a brute force algorithm and told you that it's impractical, but that's not the end, because maybe I just gave you a stupid algorithm. It's just because I told you a stupid algorithm that takes too long, that doesn't show that there isn't some much cleverer algorithm that's much quicker. Unfortunately, even that seems to be untrue. Because I say seems to be because at this point there's a very famous problem for which you'll get $1 million if you can solve it, which asks whether P equals NP. I'd love to spend half an hour just telling you all about that problem. I'm not going to. I'll just say that the moral that you can draw from that problem is that it is almost certainly the case that there is no reasonably practical algorithm for determining whether there is a proof that uses at most n symbols for a given mathematical problem. When I say almost certainly the case, everybody believes that P doesn't equal NP, apart from a few people, but almost everybody believes that if that's the case, then there is no such algorithm. But it's a major unsolved problem whether it is the case. So that really does seem to kill everything off, but I maintain that it doesn't. Because one could still ask for the following. What doesn't exist, if you believe that P doesn't equal NP, is just a short algorithm into which you can give any old mathematical problem, no matter how artificial, and it'll give you any old proof, no matter how strange, and just anything that happens to be a logically valid sequence of symbols that constitutes a valid proof would count. But that's not what maths is like for a human being. We tend to take results that somehow have some appeal, that feel natural, and we look for proofs that explain why those results are true. We don't just look for proofs that guarantee the truth of a result. We want somehow to understand why a result is true. There's a very different character to human mathematics from just arbitrary strings of symbols that happen to constitute or happen to obey certain rules and give rise to certain results. And also there's absolutely no sign that... so one of the questions I'm going to talk about today is whether humans have some magic ability that computers can never have. And so what I've just mentioned just now is the thought that it seems that there is no way for a computer to come up with a short proof of an arbitrary mathematical question if such a proof exists, but humans don't seem to be able to do that either. We don't come up with we don't guarantee to find quickly a proof of any old statement that's given to us. We tend to have, we look at a very restricted collection of statements, and often we don't manage to solve them. So So let's just try and take that into account. Let's try and come up with one final version of Hilbert's Dream that would, roughly speaking, correspond to asking for computers to do what humans can do. So what we want here is to input a mathematical statement, have a completely mechanical procedure, and what do we expect of that mechanical procedure? We expect it to give us a proof of that mathematical statement if a human being could reasonably be expected to come up with that proof. Or more generally, if the community of human mathematicians cooperatively could come up with that proof. So that's asking for something much less than we were asking before, but still a very big thing to do. I should say straight away that at the moment there is absolutely not a computer program that can do this. But I believe that there will be one day, and that's what I want to try to defend, that position. So you may have heard of the Turing test. The Turing test was another very clever thing that Turing devised, which was a test for when you would count a computer to be intelligent. And the idea is that you have two screens in front of you, and one is just connected to a computer, and the other is connected to a human who's in some room far removed from you, but connected to the computer. And you don't know which is which. And you want to try to find out. And the way you do it is by asking questions into the screen. So you type something in, and the computer will come up with some answer, and the human being will come up with answers. And the computer passes the Turing test if, after quite a while of asking questions, you find that you just don't know which was the computer and which was the human being. And there isn't a computer that can pass the Turing test yet, although there are some rather entertaining programs that can sort of pass it for about 2 minutes before you start realizing that they're being a bit monotonous or something like that. So a mathematical Turing test would be something like that, except that you restrict the questions you ask to mathematical questions. So let's consider what might happen at the moment. Supposing you were to ask a human and a computer what 32 times 64 is. A computer might do something like long multiplication, which I've written out in a slightly different form. So what does long multiplication do? It says, let's take the two final digits, multiply them together, and then we'll take the first digit of one number and the last digit of the other one, multiply them together and multiply by 10, and do the same the other way around, and then multiply the two first digits together and multiply that by 100, add the whole lot together, and here we get 2048 if we do that calculation. So that would be a mechanical method. But most human beings who've got a reasonable amount of mathematical experience, if they see what is 32 times 64, will argue in a rather different way. What they'll say is, hang on, 32, that's a power of 2, and so is 64. Thinking about it a little bit, you say, well, actually 32 is 2 to the 5, 64 is 2 to the 6, so when you multiply them together, you get 2 to the 11, remembering the rule that the powers add when you multiply the numbers together. And 2 to the 10, not everybody has this at their fingertips, but a lot of people do. 2 to the 10 is 1024, so 2 to the 11 must be 2048, and we're done. Somehow that seems better in some ways, or sort of tells you more as you're going along. And it's certainly a different way of thinking. You certainly wouldn't if you wrote 32 times 64 into a pocket calculator. There's absolutely no question of it going through the second method and saying, oh, I've just noticed that 32 and 64 are special numbers, so I'm going to do it a different way. They just don't behave like that. So if you were to ask now a typical computer what 32 times 64 was and ask it to show it's working, you might then conclude that it wasn't a human operating it from a secret room somewhere. So why do many mathematicians think that the day will never come when computers can do what they do? Here are a few answers that are typically given. One is that computers only ever do what you tell them. So you give them some very rigid instructions and it just obeys those instructions. And the one thing it can do that we can't do is maybe things like obey the same set of instructions millions of times a second or something. We aren't so good at that. But just sort of, it does very boring things fast. They're sort of like our slaves, if you see what I mean. Another thing that people often say is that computers are very good at running mechanical procedures, but at no point can they stop and look at what they're doing, step outside the whole problem, which is something that's very, very important when to human problem solving. You get a little bit stuck, and instead of just carrying on and on and on trying the same thing, you say, why am I stuck? What's going wrong here? What can I try? And you sort of try and go up a level. And another accusation is that computers, they don't sort of modify themselves. If you want a computer to get better at something, you just have to change the program. You have to do it. The computer doesn't do it by itself. Another thought is that quite a lot of the thought that goes into solving a difficult mathematics problem is rather vague and involves value judgments. This sort of looks a bit fishy to me, you might say, as a mathematician. I don't think that's going to be true. I don't really know why. It just doesn't feel right or something. That sort of thing humans say all the time. How on earth would you get a computer to say something like that? And another thing that humans do is reason visually. If you talk to mathematicians, even when they're not doing geometrical problems, they will often say that a lot of their reasoning feels very visual, and that seems to be extremely hard to get a computer to do. So there are a number of reasons that are sort of a little bit discouraging. Or discouraging if you would like to program a computer to solve maths problems, encouraging if you would like to preserve the feeling of human superiority. So it depends what your viewpoint is. Let's just consider how one might go about showing that computers could never solve maths problems as well as human beings. I think the best technique would be to argue that there's such a thing as a flash of pure genius. So sometimes it seems that a human being, when working on a maths problem, suddenly has an idea that's just amazing, and after they've had that idea, the problem becomes much easier, but it's very hard to see how they came up with the idea in the first place. And if it's very hard to see how they came up with the idea in the first place, it's very hard to imagine that there might be a mechanical procedure for coming up with that idea. So how would we actually define what a flash of pure genius is? I'm going to adopt as a working definition that a flash of pure genius is a big advance that can't be broken up into smaller and more modest advances. So if you've got an idea, very often the idea you can say, well, if somebody says, how did you think of this? You could say, well, I realized that you would have to do such and such, and that if you could do such and such, then you'd be able to do this. And already it's broken up into two smaller ideas. And then you could say, well, how did you think of the smaller idea? And there can be an answer to that, and it breaks down. But sometimes it's quite hard to work out how to break down an idea into smaller sort of sub-ideas that don't seem nearly as impressive as the original idea. Let's have an example. So what I want to give here, actually, is an example of what initially looks like a flash of pure genius, and I want to persuade you that it's not a flash of pure genius. This is I want to talk about a very nice problem. Some of you may have seen it. If you haven't seen it, I should apologize, because I'm going to spoil the problem for you by telling you the answer, which is, it's a pity because it's a lovely problem, but it's such a good illustration of what I want to talk about that it's a sacrifice I'm going to make on your behalf, whether you like it or not. So the problem is this. You have an 8 by 8 grid of squares, and you remove two opposite corners. And the question is, can you cover it with dominoes? Each domino covers two adjacent squares. Dominoes are not allowed to overlap, and you've got to cover every single square. Can you do it? Well, how does one go about thinking about such a problem? One technique is to say, well, 8 is rather big. How about looking at a smaller square, say a 2 by 2 square? Oh, no, that's not very good. A 2 by 2 square with two corners removed, you've just got two corners that touch in one. Two squares that touch in a corner. Obviously, you can't cover that. So maybe 3 by 3. No, 3 by 3 doesn't work because that leaves you with only 7 squares, and each domino covers 2 squares. So you certainly can't cover 7. But 4 by 4, maybe. 4 by 4, it's suddenly a little bit less obvious whether you can cover them. If you start doing a bit of experiment, you can say, well, let's first start with a domino that goes horizontally here, and then this one has to go down, and you can do a bit of a sort of, either this one goes this way or it goes this way, and you look at various cases, and you find that eventually you can prove that you can't do it for a 4 by 4 grid with two corners removed. But the proof is a bit nasty, and you sort of feel if you're going to come up with a proof like that that works for 6 by 6 and 8 by 8, it's just going to get more and more horrible. And it looks as though, at first, it looks as though this is really a very nasty problem because you have to consider so many cases. But it turns out So just one picture suddenly makes the answer obvious. And it's that. So here we've got not just any old 8x8 grid with two opposite corners removed, but a chessboard with two opposite corners removed. Now what's the difference between an 8x8 grid and a chessboard? Nothing much, except that the chessboard you colour squares alternately black and white. So why does that, what have black and white squares got to do with covering with dominoes? Well, if you think about it, each domino covers one black square and one white square. And if you look at the picture, you see that from the original chessboard, we've removed two black squares. Originally, there were an equal number of black and white squares, so now there are only 30 black squares and 32 white squares. So it's completely obvious that you can't cover with dominoes, because each domino covers an equal number of white and black squares. So that's a sort of superb idea. Think of it as a chessboard, and the proof more or less writes itself. And you think, well, yeah, great. So when you see solutions to problems like that, it leaves a sort of unsatisfying feeling. You think, well, it's all very well being shown the solution, but how was I ever supposed to think of a solution myself? And I will try and show you, not necessarily how you personally might have thought of one, but just how it is not completely magic that anyone ever thought of it. So let's just think of a sort of problem-solving strategy. We want to show that a grid with two corners removed can't be covered with dominoes. So one way of doing it is to try to identify some property that a grid with two opposite corners removed has, but anything that you can cover with dominoes does not have. So if that's the case, if whenever you can cover with dominoes you have such and such a property, but the grid with two opposite corners removed does not have that property, then the grid with two opposite corners can't be covered. So it's not really saying very much, but it's just a kind of general idea for a strategy of a proof. Now, there is a property that will do the job, or for which it's true, I mean, and that's the property of being coverable with dominoes. So obviously, given that the result is true, that property works, but it doesn't actually advance us in any way towards solving the problem, because how do we check that a grid with two opposite corners removed can't be covered with dominoes? That just takes us back to the problem we started with. So that doesn't really do as a property. So we want a property that's simpler than not being, simpler to check than not being coverable with dominoes. So let's think a little bit about that. What sorts of properties can we associate with arrangements of squares? So I'm talking about some arrangements of squares that are arrangements that you can cover with dominoes, and there are other arrangements that you can't, and we're trying to show that the grid with, or the depleted grid, is one of the ones you can't. So how can we associate properties with arrangements of squares? Well, one idea is to come up with some sort of numerical property. So we would like to, given an arrangement of squares, we'd like to associate some number with it, and we'd like to argue that no number that you can get with a shape that's coverable with dominoes can equal the number that you get when you take an 8x8 grid and remove two opposite corners. And one fairly simple thing, one of the first things one would try if you want to associate a number with any shape, would be to say, let's associate a number with each square, and then given any arrangement of squares, we just add up the numbers of all the squares in that arrangement. One very nice way of getting the whole proof to work would be if the number that you associate with anything that you can cover with dominoes is always the same, and the number that you get when you take a depleted grid is not that number. So what we'd like is that whatever shape we've got, if you add an extra domino to it, the number stays the same. And remember that the number is now adding up the numbers associated with all the squares in the shape. So if we want that number not to change when we add a domino, that covers two squares. So we want the number in the square, in one of the squares, to be minus the number in the other square, because otherwise the number will change when you add a domino. So what that tells us is that for every square, the number we put in the square has to be minus the number that's in all the squares next to that number. But once we've done that, that tells us we've got a square with a number in it. All the neighbouring squares have minus that number. All the squares neighbouring to those have the number again, and so on. And if we call the number black and minus the number white, then we find that we are basically building the extra structure, the sort of black-white structure that enables us to solve the problem. The only difference is that we've stuck a 1 where we used to put black and a -1 where we put white or something like that. And this is not an identical proof to the chessboard one, but it's basically the same argument. And also, if we were going to get a computer to do this, we wouldn't really want to have to the computer to have to know about things like the game of chess and colours and black and white and so on. We'd be just as happy if it came up with something to do with 1s and -1s that was clearly equivalent to the proof that a human might give. Okay, so whether you followed my verbal explanation there is not so important. I just hope that it's clear from what I said that you can break up this seeming flash of genius into smaller units, and then each of those you could start trying to break up into yet smaller units and so on. That's not to say that every single flash of genius can be broken up. It just gives one encouragement that they can. Let's go back to mental arithmetic. I've already discussed the question of what 32 times 64 is. I want to have a look at a number of different products and think about how humans might go about multiplying them if they didn't have a pen and paper and were not too rigid in the way they think. So I've already discussed this example. What about 12 times 18? If you asked me that, I would try to avoid doing long multiplication because I've noticed that 12 is multiplicatively made out of 2s and 3s, and so is 18. So it ought to be possible to do something better. So 12 is 2 times 2 times 3, and 18 is 2 times 3 times 3. So we end up with 3 2s and 3 3s, which we can also call 3 6s. So the answer is going to be 6 cubed, and 6 cubed is 216. Or if you prefer, we could just multiply the 3s together to get 27, and then double it 3 times, 54, 108, 216. So we managed to do it without long multiplication. So what about 30 times 70? Nobody in their right minds would use long multiplication for that. No human. Because they would write out a whole sort of thing and have 0 times this is 0, 0 times this is 0, and write a whole lot of noughts. But obviously the answer is to just multiply the 3 and the 7 and stick a couple of noughts on the end. What about 47 times 53? There is a stage of one's life where you're very, very attuned to any application of the formula x minus y times x plus y equals x squared minus y squared. So if you are attuned to that, you see that we've got 50 minus 3 times 50 plus 3, which is 50 squared minus 3 squared, which is 2,500 minus 9, which is 2,491. And the reason that was a good method was that 50 squared is a fairly easy thing to work out, and 3 squared is a rather small number. And so we get a fairly easy calculation to do. Much easier than doing long multiplication would have been. We could have done 12 times 18 like that, because it's 15 plus 3, 15 minus 3. 15 squared is 225. Subtract 9, 216, and we get the same answer. There's a trick for 65 times 65. If you take the square of a number that ends in 5, you take the original number and multiply by itself plus 1 and stick 25 on the end. You can check that if you've not seen that before, it's a nice little exercise to go away and work out why it works. What about 25 times 48? Here there's a nice method, which is, say 25 times 48. Well, let's just take a 2 away from the 48 and stick it on the 25. Then it becomes 50 times 24. And forget about the naught for a moment. It's sort of 5 times 24. We'll work that out and then stick a naught on the end. Well, 5 times 24, we can do the same trick again. We'll take a 2 out of the 24 and make it 12, and put it on the 5 and make that 10. So we now have 10 times 12 is 120, and put that naught back that we lost earlier on and make it that makes 1200. So there we are. That's a few human strategies. So here's just a summary of some of the methods that I used to do that. I don't know whether I need to go through that because I think I discussed them in the various examples. But the thing to notice is that they're all rather sort of ad hoc rules, and they're all sort of different. Whatever product you're given, you seem to do something different each time, and so it doesn't look like the kind of behavior that a computer could do. But I want to argue that actually that's not completely. For one thing, you could just put those instructions into a computer. Instructions more or less like that. The argument against that is, well, yes, but then somebody will come up with another example, which you'll do in another ad hoc way, and then your program won't cope with that. And that may be true. Maybe it's not. Maybe humans, sort of after a while, run out of clever tricks and just use the same ones over and over again. I think that's the case for me. If a program doesn't manage to think of every single trick going, that's not necessarily a big black mark for the program, because we get taught tricks quite a lot, so maybe one could just teach the program tricks. But actually, they're not as ad hoc as they look, some of those tricks. We can reduce them to more general things. For example, one of the things that we use a lot is associativity of multiplication. I'll come back to where I used that just now. So that's the rule that x times yz is the same as xy times z. Seems incredibly obvious, but the point is that we can actually use it to simplify calculations. And other things that we use, it's nice and easy to handle multiples of 10. So if you can modify your calculation to get a multiple of 10, that's sort of good news. Small numbers, small powers of small numbers, we like those as well. So a general strategy, which is more general than just listing the tricks that I had before, is use a few very simple principles like that in various combinations to try and make your calculation simpler. So let's just go back to the 25 times 48. What I did there was to say 25 times 2 times 24, and then I used the associativity of multiplication, the rule that the 25 times 2 times 24 is the same as 25 times 2 times 24, to rewrite it like that. And then 25 times 2 I liked, because numbers that end in 5 multiplied by 2, that's good news, because it gives us numbers that end in 0. So I sense a little bit of progress here, and it allows me to think about 5 times 24. So I'm just going through what I said earlier, and then we repeat the same trick, get 120 and put a 0 on, and get 1200. So one can get that by combining the tricks. What we were doing all the time was modifying the calculation we had to do and having some sort of sense, as we modified it, that things were getting simpler. Those are the two key things. So I've said measures of progress. So a measure of progress would be that some measure of simplicity of the calculation. If we're making the calculation look easier, that's progress. I want to go through another problem that seems frightfully clever. When you first see it, after you've seen it once or twice, it becomes a standard technique. With all standard techniques, you can still ask, how did the first person to use that technique come up with it? So let me first present the solution to the problem, roughly how big is the square root of 10,002 minus the square root of 10,001, in a sort of magic way. I'll just say, bingo, here's the answer. And what we do is we multiply the top and bottom by the square root of 10,002 plus the square root of 10,001. That sounds a bit of an odd thing to say because there isn't a top and a bottom, but unperturbed by that, we just give it a top and a bottom by just dividing by 1. We turn it into a fraction by dividing by 1. Now we can multiply top and bottom. So let's do that. So I've multiplied the top by the square root of 10,002 plus the square root of 10,001 and multiplied the bottom by the square root of 10,002 plus the square root of 10,001. And now it's our old friend x minus y times x plus y again, which gives us 10,002 minus 10,001. The 10,002 comes from the square root of 10,002 squared, and the 10,001 comes from the square root of 10,001 squared. So x here is 10,002, sorry, is the square root of 10,002, and y is the square root of 10,001. And that's very nice. 10,002 minus 10,001 is a very nice, easy number. It's just 1. And we were asking roughly how big the square root of 10,002 minus the square root of 10,001 was. And at this point, I think we can afford to approximate. So both 10,002 and 10,001 are pretty close to 10,000. 10,000 is 100 squared. So the bottom is roughly 1 over 100 plus 100. And that's 1 over 200. So 1 over 200 is, and it really is, a pretty good estimate for the square root of 10,002 minus the square root of 10,001, which was not particularly obvious when we first started, but once you've gone through this process, it is. But it looks as though something very magic has gone on. You have this idea. Why on earth do you do it? Well, it's because much later on, you get 10,002 minus 10,001 almost cancelling and giving you 1. But how on earth did anybody know that if they did this bizarre thing, it would all simplify down later on? So it looks as though it's something that you have to have some sort of genius to discover for the first time. But let me just indicate a way in which something like that could be discovered. A way of cleaning things up is to say, let's not worry about the number 10,000 because it's pretty obvious that there's nothing special about that in relation to this problem. So let's call it n. Some people prefer very concrete numbers. They feel more at home, but some people say, well, having the concrete number is distracting. Let's just call it n. So as long as you're not terrified of letters, then replacing with n is definitely makes the problem look nicer. Roughly how big is the square root of n plus 1 minus the square root of n? I could, of course, just go through the same argument, but we're trying to imagine that we don't know that argument. So if I did that, that would be very unsatisfactory. So I'm just going to write x for one of those, for the square root of n plus 1, and y for the square root of n, and just see where we go. So having written x for that and y for that, we can ask ourselves, let's just write down the facts that we know. So the main fact we know about x is that when you square it, you get n plus 1, and the main fact we know about y is that when you square it, you get n. That's what I meant by the square root. We also know that they're positive. So we don't know that much, but we know that x squared is n plus 1 and y squared is n. Now, having written that down, we look and say, is there anything we can do to simplify what we've just got? Well, there is. A reasonably natural thing to do is to try to get rid of one of the variables, and we can subtract the equation y squared equals n from the equation x squared equals n plus 1 and get rid of n. And if we get rid of n, we're surely making things a bit easier because we've only got x and y to think about, so let's do that. And what do we get? We get that x squared minus y squared equals 1. Now, at this point, the sort of I love x squared minus y squared bell rings in our mind, and we say, x squared minus y squared equals x plus y times x minus y. We don't really know why that's going to be useful, but we're stuck otherwise, so we might as well just rewrite it and see where we get. And actually, what is x minus y? Just recalling that x is the square root of n and y of n plus 1 and y is the square root of n. X minus y is precisely the quantity that we wanted to estimate. So actually, we have got somewhere by rewriting it in this way. And having done that, let's try to express everything in terms of... so what we know now is that x plus y times x minus y equals 1. Let's try to write that in terms of x minus y. It's the obvious thing to do. So we divide both sides by x plus y, and we get that the square root of n plus 1 minus the square root of n is 1 over the square root of n plus 1 plus the square root of n. And when n is large, that's more or less 1 over twice the square root of n. So it's essentially the same argument, but this time all the steps somehow emerged rather naturally just from sort of a little bit of messing around. And there wasn't some flash of genius somehow. It's just applying reasonably standard exploratory techniques in mathematics. Okay, so the fact is that people do often talk, there are whole books written about people having flashes of genius in mathematics. So am I denying that all those stories are true? Not exactly. But what I'm claiming is that they're not flashes of genius according to the definition that I've got. They're not flashes of genius that cannot be broken down. If you delve into the thought processes of the great mathematicians who've had these brilliant ideas, you'll find that an awful lot of thought went in before the flash of genius or before the brilliant idea came. However, and in particular, one of the things that what do I mean by play 20 questions? When you're trying to solve a problem, you often try things out. You say, I wonder what would happen if I did this. Would this be sensible? And so you try something out rather speculatively. Sometimes something nice happens, like some simplification happened that you didn't expect. Something cancels with something else or whatever. Sometimes you just get a mess, and in the second case, you just abandon the thing that you tried. So it's a bit like asking questions of the problem. If I do this, will it help? The problem sort of says, nope, that's not going to help. Okay, if I do this, will it help? Aha, yes. Now I look simpler after you've tried that. And so you try something else. And what you do at the end of the process is, all the questions that had a no answer, you just forget about. You sweep them under the carpet, to mix my metaphors. And all the questions that had yes answers, you present as though you just thought of one thing after another and had all this sort of stream of correct ideas that got you to the solution. Another thing that often happens in maths is that there's a sort of serendipity. You're thinking about one thing, and you suddenly realize that it solves another problem that you liked but had no idea that it was going to be useful for, that sort of thing. Or just something cancels. Later on, you realize why it must have cancelled. So when you actually come to write things, you explain in great detail why it had to cancel. But in fact, secretly, you just stumbled on this thing by accident. So that can happen quite a lot. Obviously, the more private you are, what the typical way that mathematicians work is that they work in private in the comfort of their office. They think a lot, have all these dead ends and so on, which they don't tell you about. And what's presented is a very formal sort of journal article that contains the finished product. It's a bit like, here's an analogy. Supposing somebody shows you an iPhone. You don't think, that's just magic, because, how could a single person get from 0 to an iPhone? Because they didn't get from 0 to an iPhone. They're just showing you the final product. And that's a bit what's going on with a maths paper. You see the final product, but an awful lot of work has gone into it. And generally, the less you reveal of your thought processes, the more mysterious what you produce seems to other people. And I think a lot of these things go on, that they account for the apparently magic property of some mathematical results. I haven't got much time, but I just want to talk briefly about one or two of the other difficulties that I talked about earlier on with getting computers to do maths. So one of the things was that I said that we often reason imprecisely. I want to show very briefly how I think a computer might be able to reason imprecisely in some circumstances. And the slogan that sums up what I want to say is that when we reason imprecisely, let's just stick to the case where we say, ooh, that looks a bit like that. So when we say that, we have a very precise thing that in some vague way looks like some other very precise thing. What I'd like to claim is that when that's the case, it's often possible to get a vague thing that looks exactly like another vague thing. Now, it's quite easy for a program to detect when two things are exactly the same. So this is actually quite helpful. So an example of where two things are sort of similar, there are more sophisticated examples of this by a long way, but one example you may have already seen is that factorizing numbers is in some ways a bit like factorizing polynomials. You have long division of numbers. That's a bit like long division of polynomials. If you haven't covered this, let's just say, here's an example. 168 we divide up into its prime factors. The polynomial I've written there, x to the 5 plus 8x to the 4th and so on, can be factorized as x plus 2 cubed and x squared plus 2x plus 5. Or we can think of it as x plus 2, x plus 2, x plus 2, x squared plus 2, x plus 5. And at least if we want it to be just real numbers, you can't factorize x squared plus 2x plus 5 any further. There's an analogy there that sort of can't factorize any further as a bit like a prime number that you can't factorize any further. So we sort of feel they look sort of similar in some ways. But what I want to claim is you can actually make them exactly the same if you go through a process of what I call vaguification. So you start with a statement that's precise, and then you gradually make it vaguer. So the precise statement is every positive integer can be written in exactly one way as a product of prime numbers. And then what a prime number is, it's a number that can't be written as a product of two smaller numbers, give or take a few details like whether 1 is a prime number and things. So I had this thing, if we ignore reordering. Let's just be vague about that and say it can be written in essentially one way as a product of prime numbers. Now, each time I'm putting in red the thing that is vaguer than we had in the version before. So in this third version, I've replaced positive integer by just object and prime number by basic object. And what do I mean by a basic object? I mean an object that can't be written as a product of two smaller objects. We can make that a bit vaguer. What do I mean by product of two smaller objects? I don't really know. So let's just call it a combination of two smaller objects. And now I've got a statement that's vague, but an awful lot of statements in mathematics can, if you do a similar process of vaguification, you can result in precisely the same statement. That every object can be written in essentially one way as, perhaps I should have said combination actually in the first sentence. I wrote product by mistake. So there are a lot of results in mathematics, often very different results, but they all say in one form or another that every object can be written as a combination of more basic objects, and a basic object is one that can't be written as a combination of even more basic objects. So if you do that vaguification, so here's how a program might be able to detect vague similarity. It takes two vaguely similar statements, vaguifies both of them until they become identical. Once they become identical, it says, aha, now I've got what the similarity is. And then the other thing one other thing I wanted to talk about was visual reasoning, which is something that seems hard to program into a computer. I'm not going to it would take too long. I'm not going to give a complete sort of discussion of how one might incorporate visual reasoning. I just want to take a problem and break it down into something simpler. That's the philosophy that I started with, that if you can do that, then somehow that indicates that if that process of breaking things down into simpler and simpler parts never stops, then you're okay. So I'll just show that you can start. So is there a shape that looks like a knotted bagel? I think the answer is obviously yes, or the surface of a knotted bagel. You just sort of picture it in your mind, and just to help you along, I've provided you with a picture of the surface of a knotted bagel. Once you look at that, it's completely obvious that it exists. However, if you were asked to write down a formula for the set of all points x, y, z, satisfying some condition in such a way that the set of points that satisfy that condition looked like a knotted bagel, that would be a really horrible thing to be asked to do. And yet, to a human, it's completely obvious that the shape exists. So what's going on? Why do we find it so obvious? Well, one possible answer is to say we do something like this. We take a knot, it's called a trefoil knot, blow it up. What do I mean by blow it up? I just mean where it was made of string, you make it out of a pipe, let's say, that's got some thickness, and take the surface of that. Once you think of it like that, the problem reduces somehow to the question of, can you blow up curves in that way? And is there a trefoil knot? But is there a trefoil knot is somehow an easier question than is there a knotted bagel? Is there a trefoil knot? You could say, well, even this is not completely easy, but you go around like this, and where it crosses, you sort of lift it up a bit here, and then you lift it up here, so that it doesn't actually cross itself anymore, and so on. So I'm not saying that this is now a nice, easy problem for a computer. It's just easier than what we had before. And I could carry on breaking it down further, but I haven't got time. Can you read? Yes, we can see what it says. We've reduced it to something simpler. So I'll just end with a little bit of wild speculation about what might happen. I believe that these things will happen, but a lot of people disagree with me. So this comes with a health warning, what I'm about to say. However, the things where I get less and less confident as I carry on. So initially, I think this number one. I think it's just I would bet on a lot of money that this is going to happen. So maybe even I could say the thing that I really ought to do if I want to do a bet is to say how long it'll take. Let's just say I think it's fairly safe to say that this will happen within 20 years. So there we are. A program that you'll be able to feed in a maths problem. You won't have to learn some very complicated language to tell the computer the problem. You can tell it in roughly the form that it would be in a maths textbook. And the program wouldn't necessarily solve the problem, but what it would be able to do would be solve the problem if it's the kind of problem that humans find very straightforward. I don't just mean things like solving quadratic equations, for which we've got already written algorithms, but also problems that are of the form, is this statement always true, and things like that. So if you can find proofs when humans find it really quite easy to find proofs. So very good at finding routine consequences of things, not so good when a clever idea is needed. That's roughly what I mean by that. Incidentally, even number one would be very, very useful, because what one mathematician finds a routine consequence of something, another mathematician who might not be an expert in the right area might have to spend 2 weeks thinking about before they realized that it was actually quite straightforward if you knew the right thing in the first place. So if you had a program that could find routine consequences and knew enough stuff, then it wouldn't be better than humans in their area of expertise, but it might be better than humans in somebody else's area of expertise. So that would be a very useful thing. It's a bit like, I don't know why I'm giving all these analogies, but a bit like Wikipedia or something. If you know all about something, then the Wikipedia article in that subject is not likely to help you very much. But if you just want to find out about something you don't know much about at all, it provides a very good start. So this might be a bit like a sort of intelligent Wikipedia of mathematics or something. But much better would be a program that can be taught more complicated methods for solving problems. So this program, in a way, it wouldn't be truly ingenious because you'd have to tell it how to do things. On the other hand, I think we have to be fair to the computer here. Human beings, by and large, most of what they can do in maths is stuff that they've been taught how to do. So again, we shouldn't really be too disappointed in a computer if it doesn't invent the whole of maths from scratch. So if we got a program that we can actually teach, how to do things, then that's better than just one that can do only simple things. But even better than that would be a computer that could learn from its experience. So a remarkable fact about human mathematicians that seems very hard to emulate on a computer is that they can learn how to do things just by doing one or two key or sort of well-chosen examples. If I were to give you, if you say you give a school child 4 or 5 quadratic equations and you go in detail and show them how to do it, at that point you say, well, here's another one. Can you do that? They often have the ability, if they've understood what you've said so far, to generalize from what they've seen and apply it to a new example. You don't always have to describe in general terms how to solve problems. So sometimes people can work out what the general technique is just from a few examples. And that would be even better. And then we'd sort of reach the singularity, so to speak, if you had a program that could set itself interesting problems, learn by itself, teach itself, improve itself, and become a better mathematician without any human intervention at all. So once you've got a program that can sort of develop and get better and better, then you could get into a situation where initially it can't do very much, but you leave it whirring away for a week, and you come back and suddenly it can do much harder problems than it could before. And once that's happened, I think that's sort of the end of the line for human mathematicians. But that, I think, is a long way off. So I find all this really quite exciting to think about, because for the slightly selfish reason that I think that the point at which it would put me out of business is roughly the point, or sort of beyond the point at which I'd be out of business anyway. So at that point I'll stop. Thank you very much for listening.
Totally related to some of the ones you presented is how a child or anybody might discover the notion of primeness by playing with cubes all the same size and discovering that some sets of cubes can and others cannot be arranged in a rectangle. And I think there's a very interesting question there. How do you discover that it's actually impossible as opposed to just realizing you haven't found a way yet? And I think that requires an additional kind of thinking, which is related to but different from what you were talking about.
Yes, so there are various things to separate out. There's the playing with cubes. Do you have to simulate some kind of cube playing with a computer? Another thing I would say in response just to that one example is that the question, how do you well, you sort of observe empirically that some things can't be made into rectangles, but to prove that that's impossible, and you can't really do very easily except by trial and error, because you do have to be clear that you've tried all possibilities that had any chance of working. So you have to say, well, I'll try it, not 1 by, that's putting them in a row doesn't really count, so I'll try having a 2 by something rectangle, that doesn't work, I'll try a 3 by something rectangle, that doesn't work, and then you'll go through all the possibilities, and at some point, if you're really clever, you'll notice that they're starting to get long and thin, so you're repeating the ones, so you only have to go up to the square root. But I'm not quite clear what the fact is that would be discovered.
Well, it's a bit like your mutilated chessboard problem. There you had, for that one, there was a way, you showed a way of discovering that it's impossible by finding the right way of thinking about it. And I think I leave it as an exercise. I think there's a way of thinking about the ways of rearranging cubes that can also make it obvious that it's impossible, but it requires thinking about space
So you said that if there were such a program that could, provide a proof or disproof, then mathematicians would be out of business. What, really? I mean, don't you think it would be liberating?
Well, that's a very interesting question, actually. If there were a program that could solve the kinds of problems that we spend our time solving and do it much more quickly than we could, then we would be out of what currently constitutes business. But it's not completely inconceivable that we could just say, we've got this fabulous tool now, what are we going to use it for? And it's a little bit, I don't know, one can sort of fantasize, what would we do if we had a program that could just answer any mathematical question you gave to it, or else, if it failed, you'd be pretty confident that nobody was ever going to solve it. And certainly a lot of applied maths might be pretty pleased with something like that. So what I really mean is, perhaps I could just modify what I said and just say it would radically change what mathematicians do, or what pure mathematicians do.
Okay, you said that you believe number one is going to happen in the next 20 years or so. Why do you believe number one is going to happen, and do you believe we'll ever make it to number four?
I believe one just because I've thought quite hard about a number of mathematical statements that experienced university-level mathematicians would regard as routine statements. And I've thought about how a program might be able to find proofs of those statements in roughly the way that humans do it, and it just seems to work. It doesn't seem as though it's problematic. In a way, it's almost a tautology, because you could sort of define a problem to be routine if a reasonably simple algorithm can come up with an answer to it. But then I think that the non-tautologous part of that statement is that quite a lot of statements are routine in that sense. So if that's the case, why aren't there programs out there doing it already, you might ask? And that's because there are a number of technical problems. One of them is getting this natural language input. But another is that there are an awful lot of little details about what humans do, things that we don't think about when we're doing them. Let's see if I can think of an example. Just to give one example, quite often, say we have a statement that we're going to use, like n is a prime number. At some point, we want to use the definition of what a prime number is. So we want to say sort of, therefore, since AB equals n, either A equals 1 or B equals 1 or something. But you have to decide what the appropriate moment is to use the definition of n is prime, and getting a program to decide when the right moment is to use it, rather than just sort of giving the definitions of everything right at the beginning or something, is that's the sort of thing I mean by a technical detail that makes it a little bit difficult to convert the feeling that it's obviously possible into something that actually works. But I really... Oh, and another thing is that mathematics is a big area. So I think the first step will be to find programs that can solve routine problems in one small corner of maths. And then once that can be done, then the next step will be to start finding other areas of maths that can be tackled in a similar way. And that might require a lot of work. It might require people from different areas sort of collaborating to produce a big program. So I think the reason is that it's quite a lot of work, and there are some technical problems to overcome. But that's it, really. I don't think there's a fundamental problem. With 4, I believe that it will happen, but there are definitely some really serious obstacles in the way, and I'm not saying that I see a sort of way past those obstacles. In fact, that's even true of 3. How do you get a computer to learn from experience? There are various ideas, but I think it's the ideas that convince me that it's possible, but the technical problems associated with getting those ideas to work would make the ones associated with getting 1 to work look like peanuts by comparison. So I wouldn't want to put a time frame on, certainly not on 4.
Given that computers can make mistakes extremely rarely and there can be bugs in software and stuff, would you be happier with a proof which involved no computers as opposed to one which involved, say, a significant amount of computer checking?
Well, computer checking is a different issue altogether. So I'm talking about computers finding proofs. However, I will answer this question. I'm not, but it's. I think the answer I'll give is the standard answer. There are some proofs that have now been checked by computer programs, very complicated proofs. There was one announced recently. It's called the odd order theorem, which is a huge theorem in group theory, a famous theorem. It's now been completely mechanically checked down to the last detail by a computer program. So you might ask, why do we believe that computer program more than we believe humans? And I think the answer is that empirically, humans make mistakes checking proofs far more than computers do. Also, there's a certain robustness to computer checking. If one person programs a computer to check a result and then somebody else programs a computer in a different way to check a result and they both agree with each other, then you can become really very confident in the answer. So those would be my two thoughts about that.
Given the obvious difficulty with number 4 and the generality of what you're trying to do, mightn't it be more productive, rather than working sort of from the bottom up from mathematics, to just aim at a computer that thinks like we do, and then the mathematics would follow?
Oh, you mean just sort of solve the general problem of artificial intelligence, and then maths would be a sort of corollary of that?
Yeah.
I think there are certain features. I mean, this is an important point, because I think there are certain features of mathematics that make it very much more amenable to. It avoids a number of the standard, really difficult aspects of artificial intelligence. It makes it a very good domain for trying out artificial intelligence in a situation where, I mean, to give an example of the sort of difficulty you can avoid, if you want a program that passes the general Turing test, it has to have an awful lot of general knowledge, and not just sort of knowledge of isolated facts, but how all those facts sort of link together and all that kind of thing, and that's very hard. In maths, it's somehow much less messy. The world that you're inhabiting is much smaller. You can hope to reason using just symbolic manipulation a lot more. It may be that the problem about visualization, for example, we could just avoid by coming up with symbolic things that sort of stand for visual pictures or something like that. Whereas humans interacting with the real world using their visual system in a very much more complicated way. So I think that for that reason, I prefer to go the other way. Try maths first, use the insight you get from that, and branch out into sort of full artificial intelligence.